Welcome back to Applied Algebra and Trigonometry. We will continue talking about complex numbers. During the previous video, we defined the square root of -1 as equaling j. Let's see where that takes us. Well, for starters, j equals j, and j squared would equal the square root of -1 times the square root of -1, which would be -1, which means j cubed would be j squared times j, or -1 times j, or -j. And j to the fourth would be j cubed times j, or -j times j, which would be -j squared, which is -1 times -1, which is 1. And we go around and around and around. J to the fifth would be 1 times j, or j. J to the sixth would be j times j, or -1, etc., etc. So going around and around and around. Maybe there's a mnemonic device we can use to remember this. Okay, so j to the first power gives you j. J squared equals -1. J cubed equals -j. J to the fourth equals 1. J to the fifth equals j. J to the sixth equals -1. J to the seventh equals -j. J to the eighth equals 1. J to the ninth, j to the 10th. And we can keep going infinitely. What I'd like to direct your attention to, however, is that the difference between the exponents 1 and 5 here is 4. Between 5 and 9 is 4. Between 2 and 6 is 4. In fact, between every rotation around, well, there are 4 stops on our circle, right? So add 4 to any position on this circle, add 4 to the exponent, and you are right back where you were. And that leads us to the ability to evaluate j to the 21st rather easily. Let's see. What is the largest multiple of 4 that can be subtracted? Okay, subtracted from 21. That would be j to the 20th. And if we rewrite j to the 21st as j to the 20th times j to the first, because laws of exponents tell us we can then rewrite j to the 20th as j to the fourth raised to the 5th power times j. Well, what is j to the fourth? J to the fourth is 1, and 1 times j is j. Therefore, j to the 21st is equal to j. And j to the 31st would equal, let's see, what is the largest multiple of 4 that can be subtracted from 31? That would be 28. And if we subtracted, that would leave us 3 left over. Checking, add 28 plus 3, you get 31. Okay, we're good. All right, so j to the 28th can be rewritten j to the fourth to the 7th, and then times j cubed. Well, what is j to the fourth? J to the fourth is equal to 1, and j cubed, which is what you have left over there, j cubed is -j, so we have 1 times -j, which would equal -j. Now, we could evaluate j to the 9th, and then evaluate j to the 3rd, and then multiply them and evaluate that. However, the laws of exponents and the behavior of j give us another option. This particular multiplication problem is easier if you go by the rules of exponents. We have j to the 12th, which is equal to j to the 4th cubed, which is equal to 1 cubed, which is equal to 1. So we have multiplied, we have factored. Can we add and subtract these powers of j? Let's give it a try. Well, we can't just subtract that because we have unlike terms. Let's see if we can manipulate them to get them to be like terms. Let's see, the highest power of j that is a multiple of 4 within j to the 5th is j to the 4th times j to the 1st minus j squared pretty much has to stay as it is. So we have 2 times 1 times j minus negative 1. So that would be 2j plus 1, which is still unlike terms. We cannot add those, okay? But let's talk about a conventional way to write this. It involves putting the real number first, this being the real number and this being the imaginary number. Put them together and you have a complex number, which is where we have been headed since the last video. So here's a general form of a complex number. A complex number is called complex because it is composed of two different parts. It is composed of a real part and an imaginary part. Okay, an imaginary part having the j within it, j being the square root of a negative 1. But what are a and b? Well, a and b are both elements of the real numbers. If a equals 0, then we have only b times j, a pure imaginary number. If b equals 0, we are left with a, which is a real number. So let's look at some examples of these types of numbers. For instance, we can look at 3. 3 is a real number. That means it is also a complex number. There's just no imaginary part of it. 2j is an imaginary number, sometimes called a pure imaginary number because there is no real part of this complex number. And then finally, something like 3 plus 2j, we usually do label that as a complex number. And a plus bj is also known as the rectangular form of a complex number. Please note that when writing a complex number in its rectangular form, you should always have the real part first, followed by the imaginary part. So let's play around with some radicals and some imaginary numbers. So 4 equals the square root of 8, which is equal to 4 times the square root of negative 1 times the square root of 4 times the square root of 2, which is then equal to 4 times 2 times j times the square root of 2, or 8j square root of 2. How about another example, two-part example? The square root of negative 9 times the square root of negative 16. Okay? Both of those are negative. So let's evaluate it first. Square root of negative 9 is 3j. That's multiplied by the square root of negative 16, which is 4j. So that will give us 12j squared. Oh, we've got a j squared. J squared is equal to a negative 1 times 12 is negative 12. So now let's evaluate a problem that already has the negative 9 and the negative 16 underneath the radical. This is a little different problem because since they are already there underneath the radical, we can multiply them by each other. It gives us the square root of 144, and the positive square root of 144 is 12. Those are two very different results. So let's look at an example where we're going to do some subtraction. This will be example 3. Let's look at 5 minus 2 times the square root of 25j squared. Interesting. J squared under there. We could evaluate that as -1 and continue, but it's under a square root. So let's take the square root. We have 5 minus 2. The square root of 25 is 5, and the square root of j squared is j. So we have 5 minus 10j. That's it. We have a complex number. Yes, 5 and 10j have a common factor, but why factor that out? There's nothing to cancel. We're not solving anything. We were just simplifying, and that's as simple as it gets. Another example. -3 plus the square root of -18 over 6. -3 plus -1 times the square root of 9 times the square root of 2 divided by 6. -3. Okay, we have the square root of 9 is 3. The square root of -1 is j. But then we have that radical that just will not disappear. And that's all over 6. So we have now nothing we can do on the top, but in this case, we have a denominator. Is there something we can factor out of the numerator and the denominator? Yes, we can factor out a 3. That will leave us with a plus j square root of 2 there, and we'll have 3 times 2 in the denominator. Now we can cancel those 3's, and finally this resolves as -1 plus j square root of 2 over 2. Okay, one last concept for this lesson and this video. Let's talk about a concept called the conjugate. We worked with the conjugate when we were working with radicals. Sometimes this is called the complex conjugate to differentiate it from the conjugate of a radical. When we are working with the conjugate of a complex number, what changes is the sign of the imaginary part. So the conjugate of a plus bj is a minus bj. The conjugate of -3 plus 6j is -3 minus 6j. It is the imaginary part that changes. If you only have an imaginary part, like -12j, then the sign of that imaginary part changes. If you only have the real part of a complex number, nothing changes. The real part does not change its sign. This is 156 is the conjugate of 156, but it doesn't help you very much. How does it help you? Well, that is an exercise for our next lesson. Right now, I'd just like for you to become confident in identifying conjugates. So I am done talking about complex numbers for now. I will talk to you in class.